All right, so let's get started. Um, Symmetries, or let's see where I was last time. Oh yeah, first of all, I kind of wiggle this a bit, make sure that it's being recorded or it's recording. Okay, so let's get started. Well, let's see the progress I made last time. BumperCoin spot get status. Oh wait, no, get stop status. Okay, so we have some stage changes. Let's just view that. Okay, so this must have been what I did last time. Okay, I added Scratchpad, but we didn't even do anything yet. It's an empty file, I think. So then, I guess this stuff we copied over from Connect 4 probably. Wait, what are the files? Yeah, this is just net.ts. Yeah, wait, what was the get diff? Get ignore and net.ts. Okay, fine. So then Scratchpad. Okay, fine. So then we have an example, which is the game state, a policy, a number, right? So then, oh yeah, one thing I did is like 2 streams ago, I verified that move velocity, that this function get move velocity from move direction returns the correct result by actually like writing a bunch of test code in net.ts, which I since deleted. In fact, that was the main motivation behind creating Scratchpad. So I can like, do tests, like test out these individual functions to make sure that they're working correctly and not polluting the other files, existing files. Like do all the tests, like separate the test from the code itself being tested, right? Decouple them. So anyways, the point, so one thing I noticed last stream was that this get move velocity from move direction, like this trig function, like this function that uses like trig sines and cosines basically to basically kind of get the x and y components and of course flip the y. Like this function was I'm pretty sure it was correct. Like we tested it out. I viewed the image stacks. I tested all 8 directions. But I realized last stream that like it's a bit like it rather than compute all these things every single time it's invoked, it might be better to actually just simply cache these like use caching, like simply compute all the move velocities like for all the like the directions, and then when you're actually like kind of when you're actually given a move ID and you want like the move vector, like you want the vector, the move vector, the vector velocity components, x component, y component, it might make sense to simply like pre-compute them in the beginning, and then simply just index into our cache this array right here, just index into our array or cache and just kind of index it based on like the move ID is the index, and that gives you the velocity components that you want, the x and y coordinates. So that's what I did last stream. It's a logic neutral change. It should not change any of the logic. It's just an optimization. And then here's where I guess I ended at. So again, so this train model function, right? This train model I literally just copied from Connect 4. And then basically I mentioned that like the only thing we have to do to get the train to work, like given all this like examples, is we need to implement this function here. The function here is already implemented, I believe. I mean, we haven't really tested it, but it should be implemented. Like we viewed we have viewed the image stacks, right? And then like since I've done Connect 4 already, I'm pretty confident that like I'm doing this in the same way I did that. So it's like, like we did the whole monkey see and like we're in the monkey do phase. So like convert. So anyways, so what I said was like all this stuff like seems to be like good. The only thing left is convert policy to tensor, and I believe I partially finished that. And I mentioned that convert policy to tensor will be kind of the inverse or very similar to a get policy and value function net.ts, right? Because like you need to kind of like this is the reason why like we're about to do it. Like so far all I did I did do it. Convert policy to tensor. Oh wait, did I finish it? Did I just finish everything? Oh, I think the only thing left is symmetries. Okay, let's just look at this. So basically, yeah. So like you get the so then like oh yeah, this is done. Okay, I thought I like only did these lines. I didn't realize that I actually finished it. Well, we're not sure, but oh no wonder I stopped the stream. I thought I had to use the restroom or something, and I just kind of didn't complete this. Again, it's untested. Yeah, why didn't I commit this then? I mean, I know I compiled. Actually, let me just commit this as a hopefully implement this function. But okay, let's just take a step back and review these changes. So convert policy to tensor, right? You're given a game state and a policy. Like previously, like you own, like for connect for, you only took a policy. But then here we need to also pass in the game state because the policy that we have, or sorry, to convert this to a tensor, right? Like the tensor that we get, it is like it's interpreted in the context of the game state, the coins, namely, right? Because like when we're like in the other function, like get like when what was it called, like get policy and value, which takes in the net and the game state, and it like kind of calls a predict on it. So rather than talk, let's just actually open up net.ts, right? So this function right here, like what I'm saying is like this get policy and value, like the actual policy that we're extracting, like from the model, like the neural network, we kind of like predict it, like we pass in the game state as the input, like we'll obviously convert it to image stock or convert it to tensor. And then we kind of like get the prediction, the models that predict input, we extract the policy data from it. And then what I'm saying is a policy data, like the numbers in the policy data, like the indices of the values, they only kind of make sense, or they're only like we need the game states, like the coin's coordinates, to extract the policy, like the policy from it. Like this data itself is meaningless without like the game state, because we need to actually like iterate over all the coins in the game state, like for the current player. And then we have to extract the coordinates of the coin, and those coordinates across all the different move directions, move IDs, from 0 to 7, and like for the offsets, like we need these coordinates. Like that's the heart, like this is the discretized coordinates. Like this kind of function is the heart of this like discretization, like this game state approximate representation, right? Like I've talked so much about this like it's crucial. So like the whole point is that like the policy makes sense in the context of the game state, because we have to like look at the coin's approximate coordinates to kind of help us index into the policy data index, right? We build that like using the coin coordinates. So like this kind of formula, I guess, is, yeah, we must have also used it in the other one, which we just did, convert policy to tensor. Yeah, you see this, like this whole policy data index. Again, move ID times 300, 15 times 20, which gives us like the move offset. And then same thing. We take, so coordinates of 0 must be the row, right? Or sorry, wait, no, what am I saying? Yeah, it must be the row index. Because like we kind of like skip, like we get another offset from like the number of columns, that's the row size, times the number of rows, and then eventually press the offset here for like the column offset. So yeah, it's like y's and x's are a bit transposed. Instead of x comma y, like I think if in terms of r comma c row comma column, and then like the r is kind of like a y measurement, and like the c is more like an x measurement. So it's a bit flip-flopped. Like here it's like kind of like 0 and 1, where like the y comes first, but like in this move velocity, it's actually like the x then the y. So like there's a bit of they're a bit incongruous, but oh well. So yeah, so yeah, all I was saying now is I'm just gonna review these changes from last stream and then move on to symmetries, and then hopefully symmetry is the last thing to do and we're done. Okay, so then so like the whole point, all that talk I just did, like since like highlighting this last time or reviewing this last time, was like in Connect 4 we just take a policy, and like from that we can get a tensor. But then here we also need a game state because we need the coins in the game state, just like we did in that one function, right? The get value and get policy and value function. It's like similar to that, where we would copy the same line here. Okay, so how do we do that? How do we, like, given a policy, how do we get tensor? Well, first of all, we have to fill in all zeros, just like we do for Connect 4. And then we have to kind of go over all the coins, get all the coin coordinates, and then, get the approximate, like, get the discretized coordinates from it. And then rather than iterate over the move directions, what we do is we look at the policy, right? And from the policy, like, what is a policy? A policy is like just a list of moves and weights. So then the move itself specifies the coin ID, right? Wait, what? This is a bug. No, this is wrong. This is very wrong. We only care about the moves and probabilities in the context of this coin, right? Right. So the problem is like, let's say you have coin one, coin two, and then this move which you get, the move in the prob is for the context of coin two, but then you're iterating over coin one. Then you're kind of like pretending that like you want to launch coin one with coin two's weights. Okay. Oh, there's insect here. I don't want to kill. I'm just gonna blow it away. Okay. Okay, so yeah, so actually it's a good thing I was reviewing. Okay, so that's the thing. When I had to use the restroom, I didn't. I guess I was kind of rushing things, but yeah, it's a good thing that I paused. So now let's just quickly fix this. Actually, let me make sure that the other function, like get policy and value, is correct too, and there's no like filtering missing. So from here we're iterating again. The outer loop is for the coins, and then the move ID. So then we're iterating over all the moves, and from the tensor we're getting them. So from this this policy, or sorry, this, wait, what? Not the tensor. Well, the data sync takes the tensor and gets the vanilla, the number array, or I think like some like no, never mind, like some subset, like, sorry, never mind, some native, but whatever. We're casting, or anyway, we have the policy as just an array of numbers. And then for all the coins, and then for all the moves, like we're just kind of like like unboxing it and just kind of like, yeah, like just unboxing it like that. So basically, like the stuff we're pushing here, like the stuff that's computed here is these things right here, right? Like these numbers, like the indices that we're kind of doing are only for the context of a given coin. And so like it's like the coordinates that we're using, right? Like come from that specific coin only. So like the coin and then the moves, but like these moves are only from like the move which we build comes from like is like the moves for a given coin have the coin's ID tied to them. And then its weights are, yeah, again, derived from this coin's coordinates. So the whole point, what I'm saying is that the move has a coin ID to it, right? Like, see, move.coin ID. So we only care about the moves for a given coin. So now let's go back to fixing stuff. So what was that called? Convert policy to... Okay. So here, if move and prob of 0.coin ID equals, or I can just do not equals coin dot ID, continue. Filter out moves not for coin. Just like that. So like for a given coin, after we do all the filtering out, how many times do we actually hit this number? hit these lines, that would be 8 times, because that's how many move directions we have. Because like the policy that we extracted, the policy is each coin has 8 possible candidate moves, directions to launch from. So if we have k coins, we'll have a 8k. The policy size would be 8k, and then like k minus 1 times, we'd kind of like be like kind of skipping over stuff. Like k minus 1 times 8 times, or k minus 1 times 8. K minus 1, the whole thing wrapped in parentheses, times 8 times would be hitting this if, but then the remaining 8 times, or 1 times 8, we'd kind of be hitting here. So like we're kind of like, so like 8 times we're going to be like stuffing something in the policy data for a given coin, which is correct. We don't want to like do extra times for different ones. Sorry, I'm just, never mind. Anyways, so yeah, I think that is I think this is good. Make sure it compiles. Okay, get status, get diff is not equal to the coin ID, filter out head coin dot to make sure coin has an ID field. Yeah, it has an ID field. Okay, good. So I think we're done then for this part. Get log, or let me just copy this function name here. Copy. See the hopefully context? Hopefully finish, and then net dot. Okay, got it. Get commit. Hopefully finished net dot. Convert policy to tensor. Get status. Oops. Get rebase. I forgot to add that stuff. Is this how you do it? Squash or merge with prev. Squash use commit but mailed in the previous commit. Okay, yeah, so squash this. Okay. Hopefully finish net dot convert policy to tensor. Let's delete this one. So then pick that one and merge with, so squash this one into, okay, fine. Okay, good. Status. Let's do the previous log. What was the first message? Implement net.get move velocity from movedir. So some untested. So C6A, so implement net.get move velocity was like the last one. So that was the second to last now, and then now we have this one. Okay. Get status. Okay, great. So now we're just one commit different. Okay, so now let's get started on symmetries. So I'm not sure that I'm going to actually get started. I think I might just like kind of take some time, because I need some food soon. This is going to be a quick session. I'm just going to, I think, like right now, just talk about symmetries, like instead of like connect 4, but like kind of talk about like the symmetries needed for BumperCoins. So I realized I made a little bit of there's like a clarification I need to make. So yeah, anyways, let's just get started with the whiteboard. New board. Okay, so yeah, in Connect 4 basically, or Actually, before we talk about Connect 4, let's just talk about, like, take a big picture, like, step back and talk about abstractly for, like, alpha 0, right? Like, this way symmetries are used. So typically we have some game state S, right? And then, like, here's, like, the functions. Like, let's just take a step back and refresh the memory of, like, what symmetry and, like, the whole point of symmetry, right? Like, we can basically, like, take the state S, and then we can kind of do some, like, transformation, like flip it horizontally, vertically, rotate it, transpose it, like do some kind of geometric operation. So like we're kind of like, from S we get S prime, right? So then in Monte Carlo tree search, when we're actually like kind of in calling like the get policy and value function, like when we're taking a neural net and we're passing it in the game state, well, convert it to a tensor, but when we're passing in the game state to a neural net and getting a prediction, getting some approximation of the value and the policy for it, then rather than like doing it for the actual state, what MCTS, Monte Carlo tree search, does is it randomly selects a symmetry. Let's pretend we only have one symmetry, like flip horizontally. Well, technically there's two, the identity and flip horizontally, right? But let's just say that we're like actually using a symmetry. So then when we kind of like, when we, it's like we're given a state and we want to know two things. We want to know the policy and we want to know the value, the evaluation from the neural network. Like we want to know what the neural network so-called thinks or predicts. We want to know like the classification and regression, the regression for like what value, and then the classification of like the policies for the from the state. So rather than directly call it, like take like the neural network N and just kind of do N of S, what we instead are going to do is take N and we're going to call it on the and the Connect 4 code does this. So this is already implemented in MCT. In fact, let's just look at it, right? Oh, we don't have that file. So right here, when we're in create node, right? So right here in create node, so like we're given the game state and we're given the model, right? So like notice that like first thing we do is we choose a random symmetry, right? And then what we do is we get the policy and the value for the symmetry, the symmetric state, right? Like not the actual state. It could be the actual state if it's identity symmetry, but like we get the policy and the value, but we do it like from the game state, right? So that's why we need some function that can like take a game state and convert it to S prime. So we need like S to S prime. So like this kind of like, so like this is what we need. Like this is one operation that the symmetry should support. And then the symmetry, basically after calling N of S prime, we basically like get P prime. We get the policy, right? We get the policy, but this policy is for the flipped, the transformed game state. So we need some way to kind of restore or recover, like from this policy, we need a way to kind of get the policy from the original game state. So like for Connect 4, if we kind of like have like 3 in a row, right? If we have 3 in a row right here, it's our turn, then basically like our policy vector would look like this. And like kind of like very like something like very small, like here and like here. So it'd be like 0.900 or something, like that's how it would look, or like 0.01, 0.01, and like that's kind of how the that's like kind of like how the policy, like that's what the policy should look like for this state, right? Like this is what we're expecting. But then we do flip horizontally. So like rather than querying this, we basically like these are expectants, but what we're actually gonna get is we first flip it here. So now the policy that the network returns, it's not gonna return this, this, and this. That's absolutely wrong. Instead, what the net's gonna return, hopefully, is like this, and like this, and like this. And of course, like the value is still going to be winning. It's still going to return like 0.99, which means that the current player whose turn it is going to win. So like that, like the evaluation is unchanged, right? Like if you look at the value, like the value is just, well, negamax, so -1, but like the value is still returned as is. There's no, like, you can't transform like a constant, like a, you know, just a one, just a, yeah, just a zero dimensional, like a fixed constant. Like there's no transformation for that, right? Okay, no, I'm completely wrong. I'm very wrong with that statement. Don't forget about it. But the point is that like the value is the same, like 0.99. Like it's like basically like 0.99 is the value and that's the policy. Like this is the V and then this is the P, right? So like this value is going to be the same, right? Is this desired output. So like we take the state, we flip it, and it's like, hey, like 0.99, the current player is about to move here and win. So that's the same thing here. Like the current player is about to win. But the policy that we get is like 0.01, 0.01, and like 0.9, right? So this policy is not the same as this one. Like this policy means that, hey, like we better put it in the last column, right? But then if you're in this game state and you put it in the last column, that's such a dumb move because you want to put it in the first column. So basically you need to kind of take these numbers, you need to reverse them, you need to transform them to kind of recover from this policy P prime. You're basically kind of like deriving, like we're basically kind of transforming the policy based on the symmetry to get a policy that's applicable to the original game state, right? So that's why we need P prime to P, like some inverse policy. So let's kind of recover, like, so let's recap. So we have a symmetry, we randomly choose a symmetry, and then we kind of like take the game state and we transform the game state based on that symmetry. So now we get like a transformed game state, and we call our neural net on that. So now we have a policy and value, but not for the original game state, but for the symmetric state. And then we kind of take the policy, but then now that we have a policy for the symmetric state, how do we get the actual policy for the game state that we want? And that's where like this line comes in here. We need to like inverse the policy that we got from the symmetric state. We have to inverse it to get the original policy. So that's why we need the transform inverse. So that's why we need like this function here. So like what we need is we need like that this is a left arrow right here. Like that's for this. And then we need a P prime to P, right? And that's like for that. That's for this arrow. So like, so these two arrows like that we need them for, we need them in crate node. Like when we're trying to like query information using our neural network on our game state, and we want to kind of like bring symmetries into the mix, then we need the facilities, we need the service, we need these two kind of operations that a symmetry can do for us. Like we need the symmetry to support these two operations. So let's look at symmetry. Right? So symmetry, here's a symmetry. This goes from S to S prime, which is transform game state, which we saw in action, and we've seen this one. Now, there's only one more missing, like from P to P prime, and where's that? Well, that's used in training, right? Because like once we're given a state and a policy, like example, and a value, right? And we want to kind of like train that as a training data. What we can also do for training data is for data augmentation, is we can take like the flipped state, the transformed state, the transformed policy, and then the same value, because the value doesn't change from the context of the current player whose turn it is. And we kind of like generate like this, like from this one training example E, for example, from training example, we kind of generate E and E prime, right? So now like our kind of like our E, like kind of our list of E kind of becomes the list of like E and E prime. So like we basically like doubled our training data, right? Just by like one symmetry. So each symmetry like doubles the, like, yeah, it expands, it's called data augmentation, right? Like you see that when you're training convolutional, like for doing image recognition and stuff, how like you do some like random like flips or like you move stuff around, some translations, some like reflections to kind of like make your network more robust. So like here, like given like this state and this policy, like given like this state and this policy that we're training a network on, we can also flip the policy and then flip the state to generate this new training example. Sorry, this number should also be included in the training example because there's two heads. Like this is like, yeah. So basically like, and that's why to generate new training data, we need this policy right here from P2P prime. So this is from the perspective of Connect 4. And then now I'm just gonna like talk about like BumperCoins, how BumperCoins adds a new dimension. Like this is flip horizontally, meaning flip about the vertical midline to flip about there to get from there. That's how the flip is done. But then for BumperCoins, we'll need another horizontal flip. And I want to mention that the order of flipping doesn't count. And this is actually like what tripped me up when I realized that I actually made I spoke a lie, or I spoke something, or I was a bit misguided, I believe, or I may have spoken something wrong. So I want to correct that. And then I'm just gonna like use a whiteboard to talk about like just how we kind of like this diagram that we did for I just did for Connect 4, and I've done this like many maybe weeks or even months ago for Connect 4 when I was like wrapping up Alpha 0 for Connect 4. I talked about this stuff. I'm gonna now just do it on the whiteboard for BumperCoins, and I'm just gonna end the stream. I'm not gonna actually like start doing symmetry. That's pretty trivial, I think. Hopefully, we'll see. It's not too bad because I've done it for Connect 4 already. But I'm just gonna like talk about the symmetries in BumperCoins. I believe there's 4, including technically 3, and like 1 identity. So first of all, like there's flip horizontally. It's like in Connect 4, there's like the symmetries for Connect 4 are what? Like for C4, we have only like let's just look at the symmetries, right? The symmetries for Connect 4, Shift G, I think, to go to the bottom, are the identity and the flip horizontally symmetry. So for Connect 4, we only have like, let's call this like, or let's just call this like symmetry of H. Or let's just call this, let's just call our symmetries like just H and identity, right? H and identity. So those are our 2 symmetries, right? But now for BumperCoins, basically what I'm going to, actually my battery's about to sleep soon. How much percent? I think 10. Okay, I'm gonna have to end this stream soon. Is like now what we have is we have the identity. We have like we have horizontally just like we have in Connect 4, but we also have vertically, and this thing is new, right? So this is like a new type of symmetry, which I'm gonna like kind of like show. And then we finally have only 1 more. I first thought we had 2 more, but we only have 1 more, which is horizontally and vertically. Horizontally and vertically. So these are our like symmetries. Like, whereas in Connect 4, our symmetries is just a list of 2 things, identity and H, like just the 2 entries. Here we'll have 4. So first, what I was thinking is V plus H and H plus V, like first flip horizontal, then flip vertical, or first flip vertical and then horizontal. I realized that the order doesn't even matter. So these are our symmetries. So let me just show like an example of it, right? Let's just actually like draw it out. So basically like the way you can see that there's 4 is you only need 1 coin, like this coin right here, right? This coin here could basically kind of show up in 4 different places. One is if you flip horizontally, right? Like here's like let's just have like, we can actually draw like a Punnett square if you're like kind of into genetics, right? Like if you have like little h recessive and like big H dominant, where like little h means don't flip horizontally and big H means flip horizontally, and then like same thing for vertically, then basically you have like HV, which is just the identity, and then you have like big HV, which means like this is just like H. And then you have HV, and this is just kind of like V. Then you have HV, which is just itself. So these are kind of like from here to here. Like this is another kind of view of it where that's the same, right? So this coin here, if you flip it horizontally, where would it end up? It would end up here, right? And if you take this coin here, like this is like kind of like H, and then we can also take this coin and do a vertical flip, right? Where we can take this coin. Sorry, that was a horrible looking square, a rectangle. I mean, I could use like the rectangle feature, like probably some shape here, but yeah, shape. But I'm not going to because I'm more a freehand type of person. So here, what we're doing is to go from here to here horizontally. We flip about here, so this thing kind of goes there. Like we flip about the vertical line. That's how we like go horizontally. But to go vertically, we flip about the horizontal the horizontal midline, and that kind of like flipping about there gives us here. So that's how we kind of go vertically, right? So that's like the V. And then finally, there's the HV transformation, H plus V, where this coin here basically goes diagonal. Basically, what I'm doing is like, this is the one corner. Like basically this coin can end up in all four corners. It's ended up in this corner, and like this is the corner it starts off with. Horizontally ends up in this corner. Vertically flipped ends up in that corner. And there's one remaining corner it can go to, and that is this. Horizontal and vertical, right? So here, if we kind of flip horizontally first and we're in this state, and then we kind of flip it vertically, we end up here, right? So basically, like this is a very nice chart. In fact, like this window right here is pretty nice, pretty cool. Yeah, I'm pleased with this. So this is kind of like a visualization. So here, if we flip this one vertically, then we kind of, that's how we get this coin right here. Yeah. So this one is like V, and this one must be H. Notice how like this H is like kind of parallel to this one, and this is kind of like that. This kind of looks like vector addition to me, how H plus V. So H plus V can be visualized as first flip horizontally, then vertically, or vertically and horizontally. I don't know why, but like partial derivatives of like P, A, B, and like partial B comma A, or like sometimes like they're often the same or something. Like there's like, in fact, the tangent plane, how like we can visualize it as like going this, if you have like a point in a tangent plane approximation, it's like we can like visualize it as taking some steps given to us by the X and then some steps given to us by the Y, or like some steps from partial A and some steps from partial B, and we just add them together, or projections, or like just this notion of like splitting things into components and adding them up, and like superposition and stuff, and like independence and orthogonality, and like, yeah, so the point is, okay, so let's just add some more coins. So let's say this is one coin here, and then we have like another coin like here, and like our policy is like kind of like launch this coin like a little bit down here maybe, and this coin a lot there. So like that's kind of our policy. Then our policy, which would look like, is for horizontal. So now like let's first fill in these dots. So horizontal, actually this dot is too close to the midline. Let's bring it like more down here. Or let's say that our policy here is to move this kind of up there, and then lightly move down here maybe as like one of that. So then when we kind of like flip it horizontally, what's the new policy? Now this coin wants to kind of go down there, and this coin here, or sorry, not here, but it's more kind of this way, kind of wants to go up here. So that's like the transform policy here. Like these arrows show like the vectors have been transformed, where we're only flipping, I believe the X component, the Y component, like downwards component is still the same. But like we're now like pointing towards, like in both cases we're pointing towards the center, but now like our perspective from the center has changed. How many percentage left? 8. Okay, I have to hurry up and finish this. I'll just do all the policy flips, and I'll just kind of what we did here. I'm just gonna do for the remaining transformations and end the stream. So this coin becomes this vertically. So then where does this coin land? Again, we flip it and it becomes somewhere like, so this one, if I flip, goes here. This one flip goes about there, right? So it ends up like around here. And then it kind of, its policy is like kind of like really wants to do that. And it kind of wants to do this a bit more modest, right? And then we flip, and now let's flip this horizontally and vertically. So let's say that we flipped it vertically and we want to flip it horizontally. So flipping horizontally, kind of, it'll end up here. So it ends up like kind of here, right? Which makes sense, right? And now this one really kind of wants to go towards the center. So like that's kind of like really what it wants to do for the policy, and it kind of wants to go here, right? So now let's kind of like look at this in terms of like, so how do we get here? We can get it from vertical and horizontal. So first we flip from vertical, and I'll do the other direction afterwards and end the stream. So first we flip vertically, so this one goes here, and that one goes there, which is correct. So like these two are the results of flipping it vertically. And then same thing, the policy too, like kind of gets flipped. And then to flip horizontally, what we do is we take this and go here to end up here. And like this policy becomes that, just like how we kind of like flip the x components, but left the y's the same, right? The x component like this way kind of becomes, we flip the x components for these things, same y's. And then, so that's like one, like to get these, like get this shape, we can kind of take the v and the h, but we can also take the h and the v, where we first like do the horizontal flip to kind of like get from here to here, and the same thing with policies. And then like we flip this one vertically to get here, right? So then here, this coin vertically would go here, which is correct. And this coin here at this corner would end up in that corner, which is down there. And the policies, the x's would be the same, but the y's would flip. So the x's are so then the x's are kind of like, it still has some central tendencies, but the only difference now is that the y's flip. So like this one like kind of flips, like rather than going down, it kind of points a bit up. And this one, rather than like kind of pointing up, it points down as a consequence of the vertical flip. And that is correct. So basically this thing right here can be reached both by taking v and then h, or h and then v. So it's like commutative, whatever. A plus b is same as like h plus v is same as v plus h. It's a composition. And like one way to think about it is like, we're basically like for connect for, we're kind of like the horizontal translate, the highlight of the function is basically given by like 7 minus like column index, like plus or minus 1. I forget the thing for 0 indexing, but basically it's like kind of like 7 minus c. Whereas like for BumperCoins, it'll be like h would be like 20, which is the number of columns, like number gamestate.num calls, minus the x. And like this is kind of like the horizontal flipping operation, and vertically would have like 15, which is like the number of rows, minus y, obviously, something like this. This is what I'm thinking will be transformation. Because I said 7 minus x, right? 7 minus c for connect 4. Let's actually look at that. So for connect 4, let's look at the like horizontal flip. In fact, we have the function right here. The number of columns was 7 minus 1 minus c, right? So this is kind of how it works there. But then for BumperCoins, we don't need the minus 1 because like we're working for the raw game state and fixed point, like 20 minus that, and then converting it into the image plane like does that for us. But anyways, the point is that like there's some extra symmetry. So like we basically have 3 symmetries: horizontal, vertical, horizontal plus vertical, and of course the canonic, like the most fundamental identity. So this basically is like the picture which we're about to implement next time. Now I'm going to end the stream and charge my battery before my thing dies. And that is all for now. But I think I gave an overview of like the next steps for symmetries and also how they're used. Like we need to use like these 2 operations, state to like for the context of like Monte Carlo tree search. And then finally, when we're doing the actual training data, like this stuff, what we need to kind of like do from here to here is we also need like p to a p prime, right? Which is kind of like the inverse of this function. And ultimately all these functions that like to create them, we're going to basically like use these kind of like something that looks like that to create our actual transformations. And the policies, like these things are its own inverse too. Like 20 minus 5 gives you 15, and 20 minus 15 gives you 5, and 15 minus 5 gives you 10, and 15 minus 10 gives you 15 minus 5 gives you 10, 15 minus 10 gives you 5. So as you can see, like we can kind of rewrite this as like x plus x prime equals k. And therefore you can see that there's no distinction between x and x prime. Like you can just move this tick here. Like it doesn't really change. Like if one goes up, one must go down, and like vice versa. Like there's no like, basically it looks something like this, right? That's how the function looks like, where we only look at like this plane or something, quadrant. So yeah, anyways, I'm just gonna end here because the battery's almost dead. So yeah, I mean, let me just delete this kind of garbage I just wrote, clean it up. Oops, let's bring that back. So yeah, so here's the the big picture of the symmetries, and this is what is to do next time. And then I think after that we should be done, and we can actually start training. So it's like fingers crossed that all this works. So yeah, I'll stop now, and maybe use Scratchpad later. But anyway, symmetries next time. I will end it here. And notice